Welcome back to compiler construction. In today's lecture, we'll take a look at another part which is important for code generation, especially for efficient code generation, and this is register allocation. So, in 3-address code so far, we have just assigned a new number for each and any variable, or a new name for each and any variable that we've used. However, when we want to generate real-world assembly code, it's essential that we actually make use of the processor registers and on the other hand also to efficiently handle memory. So the idea here is really to keep as many variables in registers for as much time as possible, since an access to memory takes, well, quite a bit longer than an access to registers. Depending on if your value is cached or non-cached, it might take like an order or 2 orders of magnitude longer. So whereas a register can always be accessed in one clock cycle, it might take several hundreds of clock cycles to actually access a variable in RAM if it's not cached. So one problem we have here is that the number of registers in a processor is usually very limited. So for example, we only had 4 general purpose usable registers in early x86 processors. Nowadays the situation has become a bit better. We have 16 available registers in x86 64 processors and 32 up to 32 in like ARM or RISC-V processors, current ones. But the problem is, if you have more variables than registers, you need to decide which of these variables you actually keep in registers, which others you don't keep in registers, and when a register can actually be reused for a different variable. So a very straightforward and simple solution would be just to ignore registers as much as possible. So we could just put every variable directly in the activation record for its function, or in the global data section for global variables, obviously. And for each of the instructions we execute, we would first load the operands from memory into the registers, then do the operation on these variables like an addition or something like this. So we combine the registers into a new value, and then we write the variables back into the activation record into memory. And so if we use this variable right after that instruction again, then we would have to load this again from memory. And this is obviously completely unnecessary because that value was still contained in one of the processor registers. So in turn, this straightforward solution works, and it's very easy to generate from your intermediate representation code, but it generates a large number of redundant instructions to move or copy data from memory to registers or the other way around. And well, as a consequence, it generates constant memory traffic. And if you consider a typical RISC pipeline, for example, a 5-stage pipeline, where you have like an instruction fetch and some memory access phase, if you don't have separate caches, for example, these accesses would then interfere, so your pipeline would be blocked and your code would be even slower than it already is due to the memory read and write operations, because you'd also have pipeline conflicts. So that's obviously something we should want to optimize for. So the idea behind performing register allocation in a compiler backend is to keep variables in registers as long as possible. So in the best of cases, a variable can always be in a register, and if it cannot be in a register, we need to have a predefined place to store the value of that variable if the register we assign to that variable should be reused for another variable. And obviously there are some heuristics involved. So for example, we should try to place those variables in registers which are used most often or most frequently. So we need to ask ourselves what values can actually be stored in registers. And this obviously depends on the number of registers. So when you have a large number of local variables, for example, and a small number of registers, there's a high, what we call register pressure. So there's always new values coming in because you have new expressions and operations to perform, which need space in a register. So you have to kick another value out of that register. And if you actually know this value is reused later on, you have to store it to memory and then later on load it to a register again. Some variables are difficult to store in registers. So one example is you can't actually generate a pointer to a register because a register does not have any special memory address in most processors. There are some exceptions for these in 1980s style processors, but general purpose processors today do not allow to have pointers to registers. So we actually have to perform this optimization here. And what's driving our register allocation optimization is the idea that, well, is pretty obvious. So two variables can't share the same register if they are live at the same time. So essentially we have to create an overview of dependencies of variables, so which variables are live at the same time. And we know if both variables should go into registers, then we need separate registers for storing these variables. So our basic approach for register allocation looks like this. First, we perform a live variable analysis, and you've already seen how this works. And then you go through the sets of live variables, and when two of these variables appear in the same set, we say that they interfere. On the other hand, when two variables don't interfere, we know that their live ranges are disjoint. And two variables that don't interfere, for these it's actually possible to have them share the same register because we know that their values are not required at the same time. So we can switch the register use between using it for the first variable and then switch over to using it for the second variable, as long as we can be sure that these variables don't interfere so that they're not used simultaneously. And in order to make this analysis easy for us, we use graphs once more. So graph processing, again, is a very important part of building compilers, as you've seen already. And this type of graph we're building here is a so-called interference graph. So an interference graph is a graph where we have nodes, and each variable is represented by a node, and nodes are connected by edges to actually indicate that these variables interfere. So in our example code here, we have a number of instructions here. So we have b equals a plus 2. So a was live before because we're using its value here. Afterwards, we know a and b are live because we're returning a down here, and b is also used in the next instruction. So after the second instruction, b is dead because we're reassigning it here, but we have a new value assigned to c. And finally, after our third instruction here, we have b and a still alive. C is no longer alive because we're not using it before we are returning from that function. So if we take a look at our interference graph, we just look at each of the sets for each of the instructions here. And so we see that we have an interference between a and b, so they're live at the same time here and also down here. So we get this edge in our graph here. And we have another interference between a and c in this second instruction here. So this creates this edge here. But in this piece of code, we do not have a situation where b and c would be used at the same time in our, well, abstract 3-address code here on the left-hand side. So we don't have an edge connecting b and c, and this means that we can store b and c in the same register. Of course, we still have to take care of storing the value of b to memory, maybe if we would need it later. But in this case, obviously, we're on the safe side. So in order to determine which variable can go into which register, we're doing something that's called graph coloring. So essentially, we are assigning a color to each node of the graph. And this interference graph now has one constraint. And this constraint is that two nodes that are directly connected by an edge are not allowed to have the same color. So if we do this graph coloring here and we try to minimize the number of colors used for that graph, then we automatically get an assignment to distinct classes of registers, and each of these classes of registers colored by the same color here can be assigned to one register. So for example, in our very simple graph here, we could assign variable A, which interferes with B and C, to its own register RAX. And since B and C never interfere in our little piece of code, we can assign them the same register, but it needs to be a different one from the one we store A in. So we could store B and C in the BX register of our x86 CPU. So what's this graph coloring all about? Why are we assigning colors? Well, we wouldn't need to assign colors for graphs. We could, of course, also assign them just names for classes and so on. So the background for graph coloring comes actually from people who were creating maps, so real maps of countries and cities and so on. And one very prominent problem in graph coloring is actually the problem of coloring maps. So there was a long-standing theorem that for any regular map where well, you have countries close to each other, but also several countries meeting in one point or something like this, that you only need 4 colors to actually color any arbitrary of these maps. And this sounds very simple to prove, but it is not, because countries can have so many arbitrary forms and shapes, obviously. And so this was one of the most complex proofs in graph theory so far. And this is a proof that was actually only able to be generated with the help of a computer, and that was one of the first large-scale computer-generated proofs, I think sometime back in the 1990s. And it took many, many thousands of hours of compute time to actually help building this proof that actually it's possible to color each arbitrary map of countries with only 4 different colors. And of course, what was done is these country maps were just mapped to a graph. So whenever 2 countries in a map share a border, then we have an edge in our graph, so the countries are represented by the nodes. A border is represented by an edge. And if 2 countries don't share a border, they're not connected. So a very similar problem to the problem we have here in register allocation. So this is a very classic computer science problem, and we're applying it here to a real world problem here. So even if you thought, oh yeah, coloring stuff, it's like a children's book problem in coloring books. Yes, it is, but like kids may do it intuitively right, or they don't really care if 2 adjacent areas are colored with the same color. For register allocation, we obviously have to take quite a bit of care about this. So for graph coloring in our register allocation case, if we have k registers, then the question of whether each variable can have its own register is just identical to the question if the interference graph of our registers is actually colorable with only k colors. And if we have more colors, or if we find out that we need more colors to color our graph, then we have registers, then we need to spill variables to memory whenever it's required. But we need, or we want to reduce this amount of spilling as far as possible. Now, unfortunately, as I said, this is a very complex problem. Essentially, it's an NP-complete problem, this k-colorability of graphs. So finding an optimal solution, as far as we know today, takes exponential time unless you find a better solution, which would probably give you a Turing Award. Well, don't count on it, I'd say. Nevertheless, we can still do a pretty good approximation using a good but obviously still imperfect heuristic here. So how can we perform k-coloring of graphs without wasting too much time in our compiler backend by having exponentially rising compiler backend code generation times with the number of variables that I used, which is obviously something you wouldn't want. So the first thing we do is we simplify our graph. So we try to find a node that has at most k minus 1 edges for k colorability. And then we remove it from our graph and put it on a stack. And we repeat this process until our simplified graph is trivially k-colorable, or, well, until there's no nodes left, whatever you prefer. And then step by step we start to reintroduce the nodes. So we're adding the nodes back in reverse order of our simplification. So that's why we put them on the stack. So we have a LIFO principle. So the last one we put in the stack is obviously the first one we take out of the stack again. So we can just use standard push and pop operations on a stack data type to perform this. And then we start coloring these nodes we've popped up the stack with colors that they don't actually interfere with. And then we just hope that the total number of colors is actually equal to k or less than k. So let's look at a simple example here. We have this graph on the top left hand side here consisting of 4 nodes and a couple of edges here, and we want to figure out if this graph is 3 colorable. Well, that's easy obviously to find out if you just take a closer look at the graph, but nevertheless it serves as a good example for our simplification and then construction approach again. So as I said, the first thing we do, we remove one of the nodes that has k minus 1 edges, and this node we're removing here is node B. So we not only remove node B, but of course we remove all the edges attached to node B, push B on our stack here. This leaves us with our graph here. So then the next thing we do is we remove one of the additional nodes here. So in this case we remove node A, push node A on the stack, leaving us with our simple graph here. And finally we push yet another node on the graph. Let's say we choose node C here. So this is the final step in our simplification. So we put node C on the stack, and this just leaves us with our node D here. So we can start coloring node D. Let's say we color it that way here in green. And then we can actually reconstruct our graph, obviously also reconstructing not only the nodes, but also the edges to interconnect the graph. So whenever we add a node here, we have to make sure that actually we give it a different color. So when we pop C from our graph here, we add it to our graph again, including the edge connecting the two, and give it a different color here. Then we add yet another node, A, and we also add it here, give it yet another color here, so we have 3 colors in our graph. And now finally, when we add our last node B, which was the first one we removed, we see, okay, B is not in any way related or connected to D, so we can give B the same color as D again. So our reconstruction actually shows that we could use 3 colors only to successfully color our simple graph here. So this was an example that worked pretty well, but of course sometimes this can also fail. Like if we extended our graph to have this structure here, then our algorithm will find a form where every node in our graph has k or more neighbors, because otherwise there would be a color to spare, which we could assign to this new neighbor here. So if we have this graph here, without our gray node here, this graph would still be 3 colorable, because that new node we introduced over here is not connected to the yellow one up here in any way, so we could reuse that yellow color here for our new node. But if we had that additional node here, which is connected by 3 edges to 3 nodes, each having a different color here, then this obviously is no longer 3 colorable, because the 3 neighbors of our gray node here now have used up all the 3 colors. So in order to avoid any interference, we would have to give this new node a different color. However, this does not always imply that a node that has k or more neighbors is not 3 colorable in this case. So let's look at this example graph here, where our node in the middle here obviously has 4 neighbors here in each direction. But since these other neighbors are not interconnected in any way, it's completely sufficient, for example, to use 3 colors to color that graph. And for that simple case, obviously, You would also get away with only using two colors to color the graph. So what can we do when we find out, using our graph coloring, our register interference analysis, that all nodes have k or more neighbors? Well, then obviously we'll have to make space for one of the variables we need to operate on. So we need to kick another variable out of a register, and in many cases we just can't throw the value immediately away by just overriding it, but we have to store it to memory. And this process of storing a variable from a register into an assigned memory location is called spilling. So we have an overflow of registers. We need more registers than we have available. So we're spilling one or more of the register values out to memory, which is of course an expensive operation. So this place, as we've already mentioned, to spill this variable to is usually for local variables a place in the stack frame, so in the activation record of the function or of the local block, whatever you consider, or obviously if you have a global variable, it's some location in your global data segment. And then you would remove that value from your interference graph after you pushed it on the stack. And obviously you should try to actually spill those variables which see little use, because they won't be frequently have to be reloaded from memory into register, but only rarely. So this saves you overhead by reducing the number of memory accesses. So when you want to perform spilling, well, you need some additional instructions, obviously, to move spilled variables back and forth from and to the activation record. And you could use this very simple approach actually to ensure that there's always at least a free register. So you could try to keep a few extra registers free for just shuffling data in the register and out of the registers again, in a risk so low to modify store way, where you can't directly access memory when you do operations on variables. Now a better approach would be to rewrite your low-level intermediate representation code with a new temporary variable, and then to re-perform liveness and register allocation. But of course, that's much more work to implement. So we certainly don't expect you to do this for your compiler. But of course, we want to mention that there's a better way than this simple and very obvious solution. Now, this all sounds pretty easy. Still, even if you have to do this register coloring, you can use the heuristics approach in order to get a good approximation, and then the challenge is really to spill as few variables to memory as actually possible. Now, in real-world processes, you can actually run into some difficulties here. For example, you have some conventions here, like a return value always goes into RAX. So essentially, we have to ensure that RAX can be used for a return value when you exit a function here. So some variables actually need designated registers. And you can also have different problems, like on early MIPS CPUs, you had the case that multiplication and division results didn't go into regular registers, but you had two separate registers called high and low, because a 32 by 32 bit multiplication could end up using more than 32 bits, whereas a division could actually produce a divisor, a result, and the rest of the division here. So if we actually need designated registers for variables, what we do is we treat their temporary variables as special, and we already pre-allocate their colors in the interference graph to ensure that the color actually that's assigned to a certain register, like RAX in that case, is definitely assigned to that variable. So we don't have any interference with this. And we can do a simplification here, and we can actually try to ensure that pre-colored nodes have a certain flag, so they are never actually removed from our interference graphs. So we wouldn't need to reintroduce them to get a color anyways, because they're actually already colored. So this would be a simplification. Obviously, if you have too many pre-colored variables, then you'd have a conflict, but usually the number of variables you'd have to pre-color is relatively low. And then when doing coloring, you actually use these pre-colored nodes, which indicate that they have to use a special register as a starting point when reintroducing the rest of the nodes and assigning them their separate colors. So we didn't go into too much detail on register allocation optimization here. Essentially, it's a complex topic, and to actually completely understand the theory, we would need much more time than we have available here. This would be a nice topic, for example, for an advanced course, where one could also discuss things like trying to actually use vector operations. So how do we assign parts of an array to a vector to increase processing speed and so on. But that's a bit too far for our introductory compiler course here. So let's just take a big picture of the code generation again. So what we do is we start from our low-level intermediate representation. Then, as we've seen in our previous lecture, we build a DAG of the computation where global variables are static addresses, where arguments are taken from the frame pointer, and where we assume that all local variables and temporary variables are in an infinite number of registers first. So that's what we do for building our DAG of the computation. And then we're tiling the DAG to obtain the abstract assembly. And finally, then for real assembly code generation, we would allocate registers by performing a liveness analysis of this abstract assembly code, and then finally perform our register assignment and generate the final assembly code that can actually be executed or assembled and then executed on a real processor. So this is our whole compiler process again, and we were mostly concerned with the right-hand part here. So instruction selection, register allocation are very important parts of generating our backend here. Of course, some compilers actually cheat out a bit and leave out these steps. So for example, if you have a Java compiler, actually what the Java compiler generates is code for a relatively abstract stack machine. So this stack machine doesn't really have to be concerned with real-world problems like register allocation, for example, and specific instruction selection. So in these languages using a virtual machine like Java or C# in between the compiler and the machine language, then this intermediate instructions, this bytecodes, for example, representing a stack machine for Java, they're actually then either interpreted by some code that actually just goes through the bytecode instructions piece by piece, looks at their opcodes and executes the corresponding instruction, which is very slow, or more modern compilers actually use just-in-time compilation. So what they do is they look at basic blocks in this intermediate representation, for example in Java bytecode, and then take a basic block whenever it is used, so whenever your control flow actually uses this basic block, and then it's translated on the fly to machine code. And then you have to solve all these problems again, but on a smaller scale, on a scale of a basic block, for example. So you'd have to perform instruction selection and register allocation, but it's no longer part of your high-level language compiler, which only generates bytecode, but then it's part of your just-in-time compiler that then generates real machine code. And you can also do stuff like ahead-of-time compilation, and this actually tries to analyze the Java bytecode, for example, in advance before starting a program, and then tries to translate as much as possible, so everything we know we can translate statically, into real machine code of your target architecture. And something similar is done on very many machines. So for example, the new Apple M1 chips actually have a translator from x86 machine code, so x86 were used before in Macs, to ARM machine code, and this uses a combination of static compilation and then for whatever cannot be determined statically, this is determined dynamically. And Apple does something similar. So when you for iPhones, so when you submit an application to the App Store for iPhones or iPads, what you upload nowadays is no longer a binary for the ARM processor in a phone, because Apple has so many different ARM processors in their products. But what you upload nowadays is just the intermediate representation of your compiler. Usually this compiler toolchain used by Apple is based on the Clang and LLVM compilers. So what's used there is the intermediate representation of the LLVM compiler toolchain here, and that's what you upload. And when you then download as a user an app from the App Store, what's done is that this app is actually pre-compiled for and optimized for this specific processor in your iPhone or iPad that you're using to ensure that you get an optimal, more or less optimal as possible, obviously, so an as good as possible version of the app as can be generated instead of something generic which would also run like on a 5 or 6-year-old device which doesn't have as many features as your shiny new one. So this is a compiler. Now we're not quite finished because in the final lecture that will come after that one here, we'll talk a bit more about static single assignment and how it can be used to actually optimize your code on the intermediate representation level even further. We've just kept this separate because we don't really use it intensely in our practical exercises for the compiler toolchain right now, but obviously this will be something for upcoming semesters to discuss. So that's all for today. Thanks for listening, and until next time. Bye.